Hi everyone. So in the last video we saw the principle of electromagnetic induction. That is, if you somehow change the magnetic field around a conductor, it somehow produces a current or somehow produces a voltage of some kind. Okay? So in this video we're going to sort of delve into how that happens exactly, or rather why that happens. And we're going to look at a very specific case of generating electricity, and that is when we, drag a conductor through a magnetic field at right angles. Okay, so here's a picture that we saw in the last video, and it shows us what happens to a conductor of some kind if we drag it through a magnetic field. Okay, in the first top picture, we're dragging it down through the field. Second picture, it's just in the field but not moving. Third picture, we're dragging it up through the field. And in the fourth picture, we're dragging it through the field but parallel to the field lines. Okay? Now, in the first and third pictures, those are the situations in which a current is being induced. And our job is to try and figure out, well, why that happens. Okay, why should dragging a piece of wire through a magnetic field, like we do in pictures 1 and 3, why would that produce a current at all? Okay? And it's all to do with the slap rule. Okay, so we've got to go back to fields. We've got to go back to magnetic fields in particular, and think about the direction in which charges moving through a magnetic field would experience a force. Okay, this is done using a slap rule. Okay, so let's just read these dot points, follow things step by step. It's going to be really hard for me to try and explain this to you without a video of myself with my hands making movements, but you've got to try and imagine it as best you can. Okay, so consider a short piece of conducting material. So, a piece of wire. Okay, it doesn't have to be a loop of wire, it could just be a piece of wire in general. And if we're talking about a conducting material, then we're generally talking about a metal. Okay, so think about a short piece of metal wire. Okay, metal is one of those substances which happen to have very easily movable electrons on its surface. Okay, and that's why it makes such a good electrical conductor, because the electrons can very easily move throughout the material, and it's the motion of the electrons that is basically what electricity is. Okay, now let's take that piece of wire, okay, and we're going to move it down through the magnetic field, just like in this first picture here. Okay, so we've got this piece of wire, we're moving it down through the magnetic field. Okay, now here's where we start using the slap rule. Okay, so we ourselves are in control of this piece of wire. Okay, inside the piece of wire are electrons. Okay, electrons are easily able to move around this piece of wire if they are compelled to do so. Okay, so we've got this piece of wire and we are making the electrons move in a direction that, according to this first picture, is down. Okay, if the electrons are moving downwards, okay, if the electrons are moving down, and the magnetic field in this case is to the right, then what direction force would these electrons experience? So you can use your left hand, because we're talking about electrons. So the left hand, slap rule, if the electrons are moving down, so stick your left hand out in front of you, okay? The electrons are moving down through the magnetic field, so that means your thumb is going to be pointing down in front of you, and the field lines are pointing to the right. So your fingers are pointing towards the right. So what you should have in front of you is something that looks like this. There's your thumb, and there's your fingers. Like that. Okay? And this part of your hand that's facing you, that should be the back of your hand. So your palm indicates the direction that these electrons are going to be forced to move. Okay? Now look at the picture of the loop that we've got here. Okay, so we're forcing well, I won't say force, we're making the electrons move in a downwards direction. And because the magnetic field is to the right, these electrons in this piece of wire, at least in this piece that's on the left-hand side, I'll use another color to indicate. Okay, the electrons in this piece of wire here, they will experiencing a force away from you, okay, or in this case, into the page, which you might indicate like that, going around like that, okay? So the electrons are going to want to go in a clockwise direction, yeah? That's all just due to the slap rule. The electrons are moving down through the field because we're making them move down through the field. The field is going to exert a force on them according to our slap rule that these electrons are going to want to travel in a clockwise direction around this loop, okay? Now the reason that this black arrow here is pointing in the other direction is that because this black arrow is talking about conventional current, okay? In reality, it's the electrons that are doing all the heavy lifting, okay? The electrons are the things that are moving around in your circuit, but it just simplifies things a little bit if we treat it in the opposite scenario. So we're treating it in the case that it's actually just positive charges moving around the circuit. So what you could do if you wanted to, use your right hand slap rule to determine which direction quote unquote positive charges would move around through this circuit, and you'll see that the positive charges would be forced to go in an anti-clockwise direction like that. Okay, and that would be your conventional current. Okay, but it's all to do with the slap rule. Okay, charges are moving down through the field lines point to the right, and if you want to talk about conventional current, just use your right hand and stick it out in front of you. Your right hand would look something like this. So thumb is going to point down, field is going to point to the right, so your fingers point to the right like that. And this part here, that's your palm. Okay, so your palm is facing you, which means these positive charges that we're pretending are moving around this circuit are going to travel in an anti-clockwise direction. Anti-clockwise. Okay? So it's simply just the magnetic force on the charges that's making them travel around the circuit. That's what is producing this current. That's what's producing this EMF. Okay? That's it. Okay? So look at this third dot point here. As you move the conductor down through a magnetic field, as in this picture here, according to the slap rule, okay, the negative charges, which is really actually what's going on here, the negative charges will experience a force because they're the ones that are free to move around, and they will bundle up at one end. So the negative charges are going to bundle up on this side, leaving an excess of positive charges on this side, and when you've got a situation like this, you have induced a voltage, you've induced an EMF. Okay, so this produces a potential difference in the conductor. In the second picture, here, if the conductor stops moving, then the charges stop moving. And so if the charges aren't moving in the presence of a magnetic field, they don't experience a force. So how could there be a current at all? Okay. So the key thing is that the charges move through the magnetic field, not by virtue of some kind of current that they're that's being pumped into the wire. It's that we are moving the charges ourselves. We are grabbing this wire and we are moving the wire through the magnetic field. Okay? Because the wire contains charges, that means the charges are moving through the magnetic field. If charges move through a magnetic field, they experience a force. Which direction do they experience force in? That's determined by the slap rule. And using the slap rule, you can determine that negative charges, at least in this first picture, are going to bundle up on this side of this piece of wire that we're moving, leaving an excess of positive charges over here. And if it's all connected in terms of a circuit, then that's going to make a positive current flow around like that. Okay, in an anti-clockwise direction. And you could do it the other way around. You could drag this wire up through the magnetic field. And I encourage you to test what happens here using your slap rule again. And you should see that if you imagine positive charges are the things that are moving around, that means you can use your right hand slap rule. Your thumb is going to point upwards, the field still points to the right, and your palm would face away from you, meaning the charges are going to want to go in that direction, at least on this part of the wire here that we're dragging through. And if everything's all nice and connected, the the charges will travel all the way around the wire. Okay, and what you've done is you've induced a current. In this last picture here, moving the wire parallel to the field, well, as we know, charges moving parallel to magnetic fields don't experience a force, and that can give you a reason as to why there is no current being induced when we drag the wire in this scenario. Okay, but it's all to do with the magnetic force on a moving charge. Okay, it's just now that we are sort of causing the charges to move by dragging the charges through the field ourselves. The charge would experience a force, and that translates into a current in that piece of conducting material. Okay, here's another picture. So here's just a piece of wire. Okay, it's not a full completed circuit, it's just a piece of wire or a piece of conducting material. And if you somehow drag this piece of wire to the left through this field, that means the little charges that are inside, okay, let's just pretend it's positive charges that are moving around. So let's pretend there's a whole bunch of positive charges in here. And the positive charges, because this wire is being dragged through the field, that means the positive charges have a velocity to the left. And they're moving perpendicular through a magnetic field, which points down. So using your right hand slap rule for positive charges, thumb points left, fingers point down, stick your hand out in front of you, do it right now. Fingers point down, thumb points left, your palm is facing you. Okay, so the positive charges are going to want to be forced to this end of the conductor, leaving an excess of negative charges over here. As an aside, just remember, in reality, it's the negative charges that are moving, okay, but we always just pretend that it's the positive charges. So positive charges bunch up over here, leaving more negative charges over here. When you have something like this, you've induced an EMF, you have induced a potential difference. Okay, there is now more positive over here than over here. That's called a potential difference. So you've induced an EMF. So basically, this is almost like a little battery that you've made for yourself. And then if you could connect this to a circuit of some kind, what's going to happen is the current is going to flow in this sort of anti-clockwise direction. Okay, because you've produced a voltage difference here. It's almost like just creating a battery. Because the positive terminal of that battery is over here, current will flow out of that and into the other side. Okay, so there you go. That's why, at least dragging a piece of wire through a magnetic field, that's why it induces a current. Okay, it's all to do with the force on moving charges by a magnetic field. Okay, now there's a lot of stuff that is on this slide that's kind of unnecessary. You can read through it yourself, but basically there is a way to work out the size of the induced voltage that you induce when you drag a conducting material through a magnetic field. Okay, we'll skip to the chase. Let's just look at the equation. It's down here. So the EMF produced by dragging a conductor of length L through a magnetic field of strength B at a velocity of V is equal to VBL. Okay, I'm not going to stress too much about the derivation of this. It's not too crazy to understand. Basically, the magnetic field does work on a charge to make it move to one side of the conductor. What work is done? Well, it's force times distance. How far has the charge moved from one side of the conductor to the other? That's L. What is the magnetic force on this charge? That's QVB. And so over here, voltage is equal to work over charge, work per unit charge. Work is given by that, charge is given by Q. Q's cancel out, you're left with VBL. Okay, don't stress about the derivation. This is not really going to pop up, I hope, in an exam. I haven't really seen any questions like this on an exam. Mainly it's just the type of questions that we'll see later on where we deal with an actual generator. Okay, but if you were to get something like this, just know that a conductor of length L dragged through a magnetic field of strength B at a velocity of V gets an induced EMF of size epsilon. Let's just do a couple of questions based on this. Oops. Okay, how do I get out of this now? Cool, all right. Red ink. So, let's read the question. An aircraft flies at right angles to Earth's magnetic field, which has a strength of 5 times 10 to the negative 5 Tesla. The wingspan of the aircraft is 64 meters, and it's traveling at a speed of 990 kilometers per hour. Calculate the induced voltage across the wings of the aircraft. So, what's going on here? Basically, here's a plane from the top-down view. Okay, and it's got wings like that. Okay, and well, let me draw it a bit more relevant to the question. Let's say the wings are straight out, even though that's not what a proper aeroplane would look like. This distance here is 64 meters. Okay, the plane is traveling this way. All right, and let's say also that the magnetic field is pointing this way here. Actually, this question doesn't even make any sense. Let's pretend, for whatever reason, that the magnetic field is into the page, even though it wouldn't be, but this question wouldn't make sense otherwise. Okay, magnetic field is into the page, and the plane is flying to the right. Okay, so now our job is to calculate the induced voltage across the wings of the aircraft. So, just like in the previous question, if you drag a conductor, which in this case is the wings, through a magnetic field at right angles at some velocity, you will induce an EMF of size VBL, where V is the velocity, B is the magnetic field strength, and L is the length of this conductor. In this case, the speed that we're dragging this conductor through is basically the speed of the aircraft. Okay, and we can work it out in meters per second by dividing it by 3.6, end up with 275 meters per second. Okay, so we're dragging a conductor of length 64 meters through a magnetic field of strength 5 times 10 to the negative 5 Tesla at a speed of 275 meters per second. And our job is to work out the induced EMF in this conductor, which are just the wings. So we can now just multiply everything together. Induced voltage is 275 times 5 times 10 to the negative 5 times 64, and you end up getting something like 0.88 volts. Okay, and you can work out which side would be positive and negative if you use your slap rule. So let's say that we check which direction the positive charges in the wings are going to move. So your fingers are out of the page. I think I said into the page before, sorry. They're out of the page. Your thumb points to the right. Your palm would be pointing downwards. So the positive charges are going to bunch up on this side of the wing. The negative charges are going to bunch up on this side of the wing. And so that is the direction of your potential difference. Okay? Cool. So there's a 0.88 voltage potential difference from this side of the wings to this side. There you go. In reality, that's not going to happen because really the Earth's magnetic field is either up, down, or left or right in terms of this picture. But let's ignore that for now. Cool. All right, one more question. So the rate of fluid flow within a vessel can be measured using the induced EMF when the fluid contains charged ions. So what's going on basically is there are ions traveling through this pipe, and because ions are charged particles, they're going to be moving through this region here where there is a magnetic field. Okay, and the magnetic field would be pointing from north to south, like that. And so when the charges pass through that region, they're going to be deflected due to the magnetic force. Okay, and the positive charges will bunch up on one side, the negative charges would bunch up on the other side. And that would produce a potential difference between this electrode and this electrode. So there'd be some voltage V here. All right. So it says a small magnet and sensitive voltmeter calibrated to measure speed are used. This can be applied to measure the flow of blood which contains iron in solution in the human body. So this is an artery and blood's flowing through and there are ions in your blood. Okay, and this device is used to measure the speed at which they flow through. Okay. Now it says, if the diameter of a particular artery is 2 millimeters, the strength of the magnetic field applied is 0.1 Tesla and the measured EMF is 0.1 millivolts. What is the speed of the flow of the blood within the artery? Well, we've got all our information. Okay, this is the voltage that's being induced. This is the magnetic field strength between the two magnets. The only difference is what is the quote-unquote length of the conductor that is being quote-unquote dragged through the magnetic field. Well, it's not a conductor as such, but there will be blood flowing through this artery, which can be considered as a cylinder, and the cylinder has a diameter of 2 millimeters. So there are these charges flowing through this artery, and that can be considered your conductor. Okay, so the conductor has a length of 2 millimeters, I guess you could say. And so when you put it all together, why can't I rub that out? That's really annoying. Okay, so you put it all together, you get E equals VBL, and we're trying to solve for V. So V is equal to E over BL, and we know everything. Okay, induced voltage is 0.1 millivolts, so 0.1 times 10 to the negative 3 volts over 0.1 Tesla times the length, which is 2 millimeters, or 2 times 10 to the negative 3 meters. Put it all together, you get something on the order of 0.5 meters per second. Okay. Now, like I said before, these types of questions I haven't really seen in exams. Okay, you'll get some in your book, in the Heinemann book. You may get one or two in the checkpoints, but in an actual exam, I haven't seen these kinds of problems pop up. Okay, most of the problems to do with Area of Study 2 are to do with actual generators. Okay, and there are a whole different set of equations that we use for them. So don't stress too much if this is a bit confusing for you. It's just setting the stage for why there is a current in the first place. Okay, so that's our summary. Okay, there is a current induced in a wire because of the magnetic force. Okay, charges are moving through a magnetic field. The charges would experience a force, which means they're going to bundle up on one side of a conductor. If the conductor is connected in a circuit, then that means the current is freely able to flow from the point where the positive charges bundle up around the circuit to the other side. Okay. If you just have a little piece of conductor of length L and you move it through a magnetic field of strength B at a speed of V, you can work out the induced voltage that you create when you do that. And what you're basically doing there is you're creating a voltage source. So you're basically creating a battery that has a voltage of this value. All right. You can determine the direction of the EMF, or the current if you prefer, by using your slap rule. Okay, and you pretend that the positive charges are the ones that are feeling the force. They move through the magnetic field in a certain direction. That's your thumb. The magnetic field is your fingers, and your palm indicates the direction that that current would be in. Okay. In terms of EMF for just a section of wire, it would determine the direction that the positive charges end up moving and bunching up on one side, and that would leave an excess of negative charges on the other side, thus producing a induced voltage. Okay, cool. So we'll stop there. See you next time.